Alright, welcome back to the podcast. Mark here, doing my usual digging into tech that feels almost sci-fi, but, is actually here now. Today, it's probabilistic computing.
And Jenny here, ready to try and keep up. Probabilistic computing. Okay, off the bat, that sounds a bit like it involves chance? Gambling with bits?
Haha, well, there's definitely an element of harnessing uncertainty, but it's way more controlled than a dice roll. Think about classical computers first. They're rigid, right? Every bit is a definite 0 or a definite 1. Very precise, very deterministic.
Yep. Solid as a rock.
Then you have quantum computers, which are wild because their qubits can be in superposition, both 0 and 1 at the same time, and they get entangled. But they need these insane, cryogenically cold environments to work.
Right, like colder than outer space.
Exactly. Probabilistic computing kind of finds a middle ground. It uses something different, a p-bit. Instead of being fixed at 0 or 1, or in that delicate quantum superposition, a p-bit is designed to fluctuate continuously between 0 and 1.
Fluctuate? So it's like a coin that's just flipping over and over, constantly in motion?
Yeah, that's a good visual. And the clever part is, they don't try to get rid of this fluctuation, this noise. They harness it. It becomes the computational resource. And crucially, these p-bits can be built using standard semiconductor processes, like magnetic tunnel junctions. And they work at room temperature.
Room temperature? Okay, that's a big deal right there. No massive, expensive cooling infrastructure? That removes a significant barrier to use.
Huge barrier removed. And that plays directly into one of the things I came across that just stopped me in my tracks. A claim, specifically from a video discussing this tech, suggested probabilistic computing could offer energy efficiency up to an order of 100 million times better than contemporary high-end GPUs, like those from NVIDIA.
Wait, what? 100 million times? Mark, is that even computationally possible? Like, how does that number even make sense?
Okay, fair reaction. Let's unpack it a bit. Current high-performance GPUs are beasts, incredibly powerful, but they chew through energy. They're designed for those precise, deterministic calculations we talked about. Probabilistic computers, because they use these fluctuating p-bits and leverage thermal noise, are fundamentally different in how they solve certain kinds of problems, which can lead to enormous efficiency gains.
Okay, that certain kinds of problems bit feels important. What problems are we talking about?
This is where the magic happens. They're particularly well suited for what are known as NP-hard optimization problems. These are the tough ones. Think about trying to find the absolute most efficient delivery route visiting hundreds of different locations, or figuring out the perfect structural configuration for a complex protein and drug discovery, or optimizing a massive financial portfolio with countless variables.
Right, like the classic traveling salesman problem. The one where the number of possibilities explodes as you add stops.
Exactly. Classical computers, while powerful, often find these problems incredibly difficult because the search space for solutions is so vast. They often rely on algorithms that try to find the best answer through clever searching, but it can still take an immense amount of time and power. And while quantum annealing is a quantum method for some of these too, the hardware hurdles for quantum are still significant. Probabilistic computing approaches these problems differently. You set up these networks of connected p-bits because they're constantly fluctuating and interacting with each other. The system naturally explores different potential configurations. Over time, it tends to settle into a state that represents a very good, often the optimal, solution. It's like the system uses randomness and noise to explore the solution space in a way that's energy efficient, rather than doing step-by-step digital calculations of every possibility. Companies like Toshiba, using these MTJ-based systems I mentioned, have shown they can map and solve things like the Ising model this way, which is fundamental to understanding material properties and other complex systems.
So instead of calculating every permutation, it sort of samples them intelligently by using this inherent uncertainty? And that's why it's using way less energy?
That's the core idea. The computation is happening through the collective physical dynamics of these fluctuating components, enabled by thermal noise. You're not paying the energy cost of countless precise digital operations. And because it's built with semiconductor tech we already largely understand, it has the potential to be integrated into existing computing infrastructure much more readily than quantum hardware, which is a whole other league.
Okay, that makes a lot of sense. So it's not necessarily replacing classical processors for spreadsheets or quantum computers for truly exotic quantum physics simulations. It's carving out a niche where its unique approach is incredibly efficient for a specific, very important class of problems, and it runs at room temp and potentially uses existing manufacturing methods.
That's the vision. Now, to be fair, there are obviously challenges. Scaling these systems up to truly massive sizes is still research in progress. Developing the software that speaks the language of this stochastic, or probabilistic, logic is also an ongoing effort. And benchmarking its real-world performance and energy consumption across various real-world optimization problems against highly optimized classical systems and future generations of quantum computers, that's all still being done.
So that 100 million times number, while potentially exciting for specific cases, might not hold true for every problem or every application? We need more real-world tests?
Right. The exact number likely varies a lot depending on the specific problem and the system implementation, but the underlying principle, using noise and probability as a beneficial computational tool for energy reduction, seems very solid based on the physics, and the fact that we're already seeing prototypes solve complex problems like the IMICing model efficiently at room temperature, using materials and processes we have decades of experience with. That's a pretty positive indicator. There are even companies like 1950.ai reportedly working on combining classical computation with p-bits on the same chip to create hybrid systems, which feels like a very practical next step.
Bringing the right computational tool to the right part of the problem, all in one package, I can see that making a big difference. So this could really impact things like AI inference on small devices, where power is a huge constraint, right?
Oh, absolutely. Imagine running sophisticated AI analysis directly on a sensor or a small drone with limited battery power. Probabilistic computing could make that far more feasible. And stepping back, the sheer energy savings from tackling these large-scale optimization problems in data centers, that has a significant positive ethical and environmental impact, reducing computation's carbon footprint.
It sounds like we're talking about a technology that isn't just faster or smaller, but fundamentally helps address the energy cost of increasingly complex computation, which is something we definitely need to be thinking about.
Precisely. It feels like a really important piece of the future computing puzzle. A bridge technology, in a way, that can potentially deliver some of the benefits we hope to get from quantum computing for certain problems, but with hardware that might be here sooner and integrate more easily. Who knew a bit of uncertainty could be so computationally powerful?
Right? It's counterintuitive but fascinating. I'm definitely keeping an eye on this space now. Thanks for shedding some light on it, Mark.
Anytime, Jenny. Still lots of research happening, lots of challenges ahead, but the initial results are, dare I say, quite encouraging. The world of tech keeps throwing curveballs.
It certainly does. All right, everyone, that's it for this episode. See you next time.